Hello students, now we will see the second problem of process synchronization, that is readers writers problem. Okay, so in readers writers problem, the reader and the writer share a data set. It can be a file in this case. Okay, so a reader can only read from the file, that is it does not have to perform any updates. Okay, writers can both read and write. So here, that is why, since readers can only read, we can allow multiple readers to read at the same time. But the problem is with respect to a writer, because only a single writer can access the shared data at a time. You cannot let a writer and one more writer share the same data. You cannot let a reader and a writer do perform action together, or a writer or reader perform an action together. But you can let reader and reader access the critical section together. Okay, so that is the problem. We cannot let more than one writer or a reader writer or a writer reader to access the critical section. Now, shared data here is the data set. It can be a file or it can be a resource. Clear? Yeah. So here we have two semaphores. One is mutex, which is always initialized to 1, and one is WRT, which is initialized to 1. There is a integer, that is read count, which is initialized to 0. This variable keeps the count of number of reader process. Okay, so you can call that this mutex is safeguarding this read count. So this read count variable, that is an integer, is safeguarded by the semaphore mutex. Okay, let us now see the structure of a writer process. Yeah, okay, so this is a writer process, very simple. Okay, so as I said, only one writer can be writing at a point of time. Clear? So let me take an example. If there is a writer which wants to enter to its critical section, that means it wants to perform writing into this file. Okay, okay, I mean writer. Okay, so writer wants to write to this file. Okay, so what is the actual value of WRT? WRT is initialized to 1. So whenever a writer wants to write into a particular file, it will execute this wait operation. That is, wait will basically decrement the value of WRT. So this becomes 0 when it is decremented. So when it is decremented, the time write will write into this file, that is writing operation is performed. After it finishes off, it will signal WRT, that is 0 will be incremented to 1, that is the other write can come. Now let me assume that this write was writing into a file. At the same time, one more write, this is write 1 and this is write 2. So write 1 is writing into this file. At the same time, W2, which is the writer file, also wants to access its critical section. So let us consider this case. So what is the value of W now? 0, because writer 1 is executing. That means it has set its writer value to 0. It has not still come out. Okay, so the WRT value is still 0. So when W2 tries to check with the wait operation here, it finds that WRT is 0. So if it tries to decrement it, it gives you a negative value, which means it will not allow W2 to enter into the file. This is how more than one writer is prevented from accessing the shared resource. Now let us see the structure of a reader process. Okay, so this is the structure of reader process. Fine, this is a infinite while condition. Clear? Okay, now, so as I said, you can see read count is safeguarded by mutex. Read count is safeguarded by mutex. Okay, so let me write some values here. M, this is WRT, and this is read count. Okay, yeah. Now initially, you know that the value of mutex is 1, WRT is 1, and what about the read count? The read count is initialized to 0 initially. Okay, now this is a file. Yeah, this is a file. Now let's consider that there is a reader process that wants to read the file. So what happens to wait mutex? Wait mutex is decremented, which becomes 0. And then what about the value of count? The value of count is increased to 1. That means there is a condition here, if reader count is equal to 1. So now the reader count is equal to 1. What should you do? So you know that when the reader count wants to perform a reading operation, then there should not be any other writing process, that is writing into the file. You know it, right? So that means what? If the first process is going to be reader, then it has to check if there is an already existing writer process which is writing into this particular file. So this is what it checks, because if the reader is the first process, okay, that means there can be a writing process which is writing into the file, right? So when it is the first reader process, it checks if there is a writing process already writing into a file. Let's now assume that there is no writing process. That means what, guys? The value of WRT is 1, right? So if there is no writing process, then definitely WRT will be 1. Only if there is an already existing writing process, then the WRT value is going to be 0, right? So here we find that the value of WRT is 1, and when it executes wait, the WRT is going to be set to 0. That is when this reader can get into the file, that is it can start reading the file, and then this signal is mutex, that is the mutex is signal. So this mutex will be converted to 1. Okay, so this means what? That is the only one, the reader was the first process, and when it tried to enter the critical section, it also checked if there was an already existing writer process. We found that there was no existing writer in process, that is why it could enter the critical section. If we had assumed that there was already an existing writer process, so if there was already an existing writer process, then WRT value would have been set to 0 in the previous slide, right? So in that case, this particular condition wouldn't be executed. Clear? Okay, that is what happens for reader. Now, at the second instance, let's say there is one more reader process. Okay, so reader will wait the mutex. So again mutex will be reduced to 0. What about the read count? The read count is going to be 2. That is 1 plus 1 is going to be 2. So is this condition going to satisfy? If reader count equal to 1, no, the reader count is equal to 2. That means what? There is an already existing reader process that is reading from the file. That means, as I said, if there is a reader, then the other reader also come. It is not a problem. So you don't have to check with this condition, because the previous one was a reader. Now also it is a reader. That is why the count has incremented, right? So in that case, the second reader also can read from the file. Okay. So similarly, the signal is mutex here. This is just to safeguard the count of read. Okay. Now, whatever, so both the processes or both the readers will read from the file, right? Okay, so WRT is still 0 only. Now, what about considering the readers leaving the critical section, or let's assume that they have finished reading from the file, so now they want to exit. So they will perform this operation, right? That is wait mutex. So what is wait mutex? It was 1. So let's assume that the reader wants to exit. So from 1, it converts its value to 0. And then what about read count? The count will be decremented by 1. Now again, if reader count equal to 0, which means what? If there is no reader available, then we can give a chance to the writer. That is, if reader count equal to 0, which means if there is no reader process available, then we can signal the writer process to write into the file. But right now we had 2, so 1 wants to exit. So the count of the reader count will be 1. So this condition is going to be false. Okay. So because there is an already existing one reader still in the still reading from the file. Okay. So then you signal this mutex, that is incremented to 1. This is basically to safeguard the variable read count. Then let's assume that in the fourth iteration, the other reader process also wants to come out. Okay. So when it wants to come out, again it will execute these 4 statements. So wait mutex. So wait mutex will be decremented, that is it will be 0. What about the read count? Now read count will be decremented, so it becomes 0. Okay. So when it becomes 0, let's check this condition. If reader count equal to 0, yes, now it becomes true, because the second reader also wants to exit from the 5. That is when this condition executes. That is, now we are letting the writer process to execute. If there was some writer process that was waiting to write into the file, it can execute now. Okay. So it is when it executes, and the writer process is incremented to 1, because when you increment the semaphore to 1, only then that particular process can gain access or can enter into its critical section, right? And signal is and mutex is signal. That is, from 0 it becomes 1. Okay, now see, look at this. Now we have WRT set as 1. So we went according to the sequence. Reader came first, it could enter into the critical section. A second reader came, it could also enter into the critical section. Then in the third iteration, we thought of exiting the reader from the file. So it exited, the other reader also exited. And then in the fifth iteration, now let us assume there is a writer process that has come. Okay, so when a writer process comes, if you go back to the previous slide, you can see that, if you remember, now WRT is set to 1, right, because of this one. Okay, now when writer wants to enter into the critical section, or it wants to write into the file, it will wait semaphore, which is wait semaphore, in the sense wait will be now reduced to 1. That is, this semaphore which was 1 will be reduced to 0. It can then read write into the file, and then when it wants to come out, it can execute signal mutex, right? So this is a mutex. It is WRT. Sorry, it is WRT. So it can signal WRT, and then it will be set to 1. So in the next iteration, you can let a reader come. If you can let a reader come, then you can let the other readers also come, or you can let the other writer also come. Okay, this is how the structure for reader process executes. If there is a reader, you can let other readers also read from the file. But if there is a writer, reader cannot read from the file. Vice versa. If there is a reader, then writer cannot read from the write into the file. If there is a writer, then another writer cannot write into the file. So all these statements take care of the conditions that I mentioned. I hope this is clear to you guys. We will now move on to another problem with respect to synchronization, which is dining philosopher's problem. Okay, so this problem consists of 5 philosophers and 5 chopsticks. Okay, so these 5 philosophers have only 2 jobs. They think and they eat, and they are seated in a circular dining table. Okay, so these are the philosophers, and here the blue circles that you can see are their plates, and on their left, on to the right, there are chopsticks, and there is a bowl of rice that is kept at the center. Okay, so here the share data is this bowl of rice, as well as the bowl of rice. Yes, they have to share it in common, but the share data here is chopsticks. Okay, that is, they need to use chopsticks to eat the rice from the bowl. Okay, now what about the semaphore? We totally have how many? 5 chopsticks, right? So for each of these chopsticks, we have a semaphore. That is why it's an array chopstick of 5, and all of it are initialized to 1. Let us see how this dining philosopher problem actually works. Okay, we will start naming the chopsticks or the processor. So this is 1 philosopher, this is 2 philosopher, this is 3, this is 4, and this is 5. Okay, 5th philosopher. And the chopstick is, this is 1 chopstick, this is the 2nd chopstick, this is the 3rd chopstick, this is the 4th chopstick, and this is the 5th chopstick. Okay, now here, this is with respect to a philosopher I. Yeah, so this is the infinite while condition. Okay, this is with respect to 1 philosopher I. Okay, let us consider the philosopher I to be the first philosopher, this philosopher. Okay, yeah, now, so when the philosopher I is hungry, he wants to grab his left chopstick first and then his right chopstick first. So he will grab his left chopstick first, that is chopstick of 5, which is this chopstick. Next, he will try to grab his second chopstick if it is free. So if it is free, he will try to grab the second chopstick. So this is I plus 1, which is 1 plus 1. So 2 modulo 5 is nothing but 2. So the value of this is 1, the value of this is 2. So he will try to grab his left chopstick first, and then he will try to grab his right chopstick next, if both the chopsticks are available. After that, he will finish eating. Then he will release his left chopstick, and then he will release his right chopstick, and then start thinking again, so that the other philosopher can begin eating. Okay, so this process continues. But there is a problem with this particular dining philosopher scenario here. See, let's assume that if every particular philosopher grabs his left chopstick, okay, all of them grab their left chopstick. That is, one grabs this, and then two grabs his left chopstick, that is 2 here. 3 grabs his left chopstick, which is 3 here. So if everyone grabs their left chopsticks, then it creates a deadlock situation, because the right of every philosopher is the left chopstick of the other philosopher, right? So this results in a deadlock situation which will never be rectified. Okay, so this is a problem in dining philosophers problem. That is, when each of the philosophers plan to take their left chopsticks, that is, the other philosopher will not get its right chopstick, because their right chopsticks is actually a left chopstick to the other philosopher, right? So this results in a deadlock problem. Okay, so there are a numerous solution to avoid this deadlock. That is, we can plan of having only 3 to 4, maximum of 4 philosophers, or making sure that a particular philosopher only picks if the 2 chopsticks are available. So such solutions exist, but then we will actually see a very good solution using monitors in the next video. Okay, so these are the 3 problems of process synchronization. One is bounded buffer problem, second one is reader writer's problem, and third one is dining philosopher's problem. Okay, now here in the next slide, if you remember, you had attempted a quiz, right? And these questions were there in the quiz. So there is a problem with semaphore. That is, if there is incorrect use of the semaphore operations, right? For example, you have seen that wait is executed and then signal is executed. But what if you change the order of the operations? That is, if you have signal first and then wait first. Signal first means that it will allow all the processes to enter into the critical section. That is, if signal is put before wait, then all the processes will be allowed to enter into their critical sections, which is not correct. Now, if you try to replace both, that is, if you try to replace both the operations by wait operations, then what happens? Suppose, let's think that wait is already there in the beginning. So a process has entered into its critical section, but it is never going to come out of its critical section. That is, it is a deadlock here. It will not let the other processes come into their critical sections, because there is a wait here. If there would be a signal here, then it could have easily left and allowed the other process to come into the critical section. But this is wait. That is, it will never allow any other process to come into a critical section. So this is a deadlock situation. This is a deadlock situation. So we cannot have such order of process operations. We need to have wait initial and then signal. If you try to change the order, then it will result in these kind of problem. So omitting any one of the operation also, or omitting both the operation also, will create a problem. So we are not supposed to do this.